Okay, section 14.3 is all about the pH scale. We talk about pH all the time. Balance, pH balance, you know, it's on commercials, blah, blah, blah. So today we're going to actually talk about the mathematical calculation of pH. And it's awesome because it's all based on 14. Bang, it's pretty great. Now, before we get into the notes, just wanted to show you this. Okay, here's our autoionization of water. There we go. Okay, autoionization of water. Yep. H2O plus H2O gives you H3O plus OH minus. Our KW here is, oops, I marked it out. KW is our equilibrium constant for this special reaction. 1.0 times 10 to the negative 14. There's where the 14 comes from. KW is also written as all equilibrium rules apply. H3O plus OH minus. Okay, so this is where the origin story of the pH scale comes from, this reaction right here. All right, so let's get into it. We are picking up on page 3 of the notes handout, if you want to follow along while we go. Okay. Slideshow from current. Okay, so the pH scale, very easy, compact way to represent the hydrogen ion concentration or the hydronium ion concentration, okay? Here's the basic equation. Said basic again. Here is the pH equation. Little p, capital H. Little p, capital H, that's pH. Negative log of the H plus concentration. Remember, square brackets mean molar concentration. And we could also write H3O plus, because remember, H plus and H3O plus mean the same thing, the hydronium ion. Now, whenever you have a little p, it means negative log of that thing. So in this case, pH is the negative log of the H plus concentration. This is base 10 log, not natural log. So make sure you're using the right function on your calculator. Okay, so as the pH decreases, okay, H plus increases, okay? It goes the opposites because it's the negative log of the H plus concentration. Okay, significant figures. Okay, so for those of you, okay, again, we're not going to kill ourselves over this, but if you want to do the significant figures correctly, which I encourage, the significant figures are based on the decimal places. Okay, so for example, if our H plus concentration is 1.0 times 10 to the negative 7, that's 2 significant figures. So we're going to have 2 decimal places in our pH. So the number of significant figures determines the number of decimal places when you calculate the pH. Okay, well, we know this, right? pH range, you've probably learned this before. 7 is neutral. I don't know why this diagram isn't in the notes, but it's not. pH of a 7 is neutral, so right in the middle, where H plus and OH minus are equal. If pH is greater than 7, remember it's reversed. So if it's greater than 7, then the H plus concentration is low. So that means that you have a more basic solution, means that the H plus concentration is smaller than the OH minus concentration. If the pH is less than 7, pH goes down, H plus goes up. So therefore you have a lot of H plus in the solution, so higher hydronium ion concentration. All right, there are other things you can do with this. Okay, remember I just said little p means negative log. So if we have POH, that means the negative log of the hydroxide ion concentration. Okay, now here's some handy little equations. pH plus POH is equal to 14. H plus times OH minus is equal to 1 times 10 to the negative 14, which I showed you at the beginning right here. Okay? There's also pK. Okay? The little p, capital K, means the negative log of the equilibrium constant. What? Okay, we'll get to that. That's a little foreshadowing. Okay, now, there's this cute diagram. I can't figure this out. Okay, it's on page 13 of your notes handout. There we go. Okay, so if you take a flip over to page 13, you'll see this cute diagram. I like the square diagram here because it summarizes the kind of the roadmap for H plus, OH minus, POH, and pH. So it's very easy to get from one stop to the other. So if you look at the square diagram on page 13, if you start with your H plus concentration, you can take negative log and you go down to pH, okay? If you do 14 minus the pH, you get POH, okay? If you want to go from POH to OH minus, you can do 10 to the negative POH, okay? And then H plus to OH minus, you use the KW expression, 1 times 10 to the negative 14. Okay, so I highly encourage you to use this little diagram to help you as you're manipulating, as you're working your way through these calculations. Another place you can go is our handy dandy equation sheet, AP equation sheet. Yep, there goes. So the pH equations are all on the equation sheet in the equilibrium section. So if you look there, and this is your tool that you're going to have on the exams and the tests. It tells you here in the middle pH, it gives you the pH equation, gives you POH equation, and then Ka, Kb, we'll get back to that later, pKa, pKb. Okay, so, it also tells you that pKw is 14, and that's also equal to pH plus POH. All the equations that you just wrote down in your notes are on the equation sheet. So let's use that sucker. Okay, so we're going to do our first example here, calculating pH of a strong acid. So we know a strong acid completely dissociates into H plus and an anion, okay? So what we can do there is it's not an equilibrium system. We're going to consider a strong acid to be completely dissociated, okay? So in our example, we want to know the pH of a 0.25 molar solution of hydrochloric acid. So essentially what's happening here is the HCl and the water are coming together, and the HCl is giving every single one of its H pluses to the water. So we get hydronium ion and Cl minus. Or you could just write it like this. HCl completely dissociates into H plus or Cl minus. Both of those equations say the same thing. You can pick which one you like. For our pH calculation, it's pretty simple because the original concentration of the acid is equal to, because it's a 1-to-1 mole ratio, is equal to the H plus concentration. So all we've got to do is take the negative log of the acid concentration when it's a strong acid, and that gives us the pH. And notice how low the pH is, because it's a strong acid, so we would expect it to be pretty low. Okay, so far so good. Now, we're going to do a little flipsy-doodle over to page 5. So turn to page 5 in your notes. And I am going to see if I can get myself to the right slide. So we're going to do just strong acid and strong base. And then that'll set you up for all the various things I gave you to work on. Okay, so if we go here to page 5, we're just going to talk about the pH of strong bases. And that's where we're going to stop until I get back from my trip. So strong acids and strong bases. Okay, so the Arrhenius definition, strong bases produce an OH minus ion. Bronsted-Lowry, strong bases are proton acceptors. Give me that proton. Okay, strong bases, just like a strong acid, 100% dissociation. So we're going to assume that a strong base goes completely to cation and OH minus, okay? So we have to just figure out the OH minus concentration, and we can use that to calculate the pH. So here we have, these are some examples of strong bases. Anything with a hydroxide is considered a strong base, okay? Lithium hydroxide, sodium hydroxide, potassium hydroxide, group 2 elements, yep, notice there's a subscript 2 there, so we have to take that into account when we calculate the OH concentration. All right, so here's our example. So we can calculate the pH. What we have to do, what I like to do, is to calculate the POH and then subtract it from 14. You can go the other way around the square. Okay, so if you do that way, on the square, if I start with POH, take the negative log of it, OH minus negative log, I get POH 14 minus. So I'm going down the one side of the square, but you can always go the other direction and you'll end up in the same spot, okay? You could use the KW expression to get H plus and then take the negative log of the H plus ion concentration. Either way works. All right, I like this way because I think it's easier, straightforward. All right, so POH and then 14 minus the POH. So here's our example. Now, barium hydroxide, 2 OHs per formula unit. So when this dissociates, we're going to get 2 moles of OH for every 1 mole of the compound. So remember back in first semester when we were getting the molarity of solutions, you would multiply the molarity of the original solution times the subscript. And that's what we have to do here. We're going to take the molarity of the barium hydroxide and multiply it by 2 because the OH has a subscript of 2. So our OH concentration is 0.20 molar, twice the original concentration. Now this is the way I like to do it. Negative log of that gives us our POH value. Then if we do 14 minus the POH, that gives us the pH. And notice that it's very close to 14. It should be because it's a strong base. So if you were getting a low number, then that's a good clue that you skipped a step somewhere. All right, that brings us to the end of what I wanted to do to get you guys ready to do the assignments I gave you. All right, good luck, and I'll see you on Wednesday.